Now we're going to think about torque. We're going back to the same figure as before, but now we're taking our square loop in a uniform magnetic field and thinking about the angles and the lines of action. So if you imagine that it can rotate around this central axis here, so basically the x-axis is our pivot, then we see that we're not going to have any torque from the front or the back force. But the top and the bottom force actually cause a torque because they act on some distance away from the pivot point. So you get a torque that would cause it to rotate. And notice that we can write it as this cross product. And remember that mu is going to be our magnetic dipole moment. The magnitude of it is I current times the area, which in this case would be L squared. And once we say that it's a vector, it needs to be perpendicular to the loop. So this orange vector here is moment of inertia. Sorry, not moment of inertia, that was the wrong thing. The magnetic dipole moment. Now be careful, because when you have something drawn like this, I can barely understand what all of these vectors are doing when a professional artist does it. So if you're going to draw this on your homework, you probably want to do maybe a side view and a top view or an edge view. Don't necessarily try to draw it three-dimensionally because it's going to be really confusing. So now remember that this is a cross product. So we can say that the magnitude of our torque is going to be mu times b sine, and here I'm going to call it theta because that's the value they used here rather than alpha. So if they're parallel, you get no torque. What that means is if your magnetic field, notice I'm about to do an edge view, is to the side, so that's your B field, and it's again uniform. Notice that this is for a uniform field. We're not going to think about torque in a non-uniform sense. We're now looking edge on, right? So this is the edge of our little loop. That means that mu, our magnetic dipole moment, is also to the right. So those are parallel. Theta equals 0, sine of 0 is 0. In this case, your torque is equal to 0. So please keep that in mind, that you can have a torque, but it depends on how it's oriented. So in this case, you have 0 torque. If it's actually perpendicular to the magnetic field, then you have maximal torque. If it is flipped completely anti-parallel, you have 0 torque, but it's an unstable equilibrium. So if we had it oriented instead facing this way, then if you tilted it at all, it would immediately rotate, but in this situation, there's technically 0 torque. So this is like balancing, this situation is like balancing a pencil on its tip. Theoretically, it's possible, but any slight movement will make it flip around. So this is your stable equilibrium. This is an unstable equilibrium.